Hi everybody, Physics Ninja here. Today I have a really nice problem for you. I have a charge Q inside a cylinder and I want to calculate the electric flux through the different surfaces of this cylinder. For example, we might have the side wall of that cylinder, how much electric flux is going through that surface, and maybe I can compare it to the ends of that cylinder. And at the end, if I add them all up, then I know I should be able to apply Gauss's law to that problem. Okay, so we're going to show you how to set up the integrals. In this case, it's a little bit complicated because the field is not constant on that surface. So you do have to integrate this problem, which is what makes it complicated. So I'm going to show you how to set that up and solve this problem. Like with all my videos, if you like it, give it a thumbs up. Consider subscribing to my channel. Okay, let's get started. All right, the first thing we're going to consider is the field produced by this point charge Q. It's positive. If I look at any point, for example, on the surface at the top, that would produce an electric field that has a direction like this. And again, for the first part, I'm considering only the tube part. I want to calculate the electric flux through the tube, which means I really want to evaluate this expression, right? The total electric flux, I have to integrate just over the tube part, the side wall, of this expression, E, the scalar product with the area. Okay, so we first start by considering the field produced by a point charge. Right, that is a pretty straightforward expression. The field, just the magnitude of it anyway, is K Q divided by the distance squared. All right, so the distance squared is this guy, right, where that dashed line is. So let's go ahead and define some things. So the point from the charge along this x-axis here, I'm just going to call that x. Now the radius of this tube is r. So that means that this guy here would be r squared plus x squared. Okay, so if you substitute that in the field expression, again, you're simply going to get x squared plus r squared in the denominator. Remember, that expression is squared, so that took care of that square root term. Now, the other thing that is important for the flux, again, if you evaluate this, that scalar product right here, that means that you're really only interested in the magnitudes of those vectors, right? So it's E cos of the angle theta, that's that scalar product, and with that vector dA. So at the end, you get rid of that scalar product and you write it out as something like this. So where is that angle phi defined, and where is this vector dA defined? Let's go ahead and do that. So again, dA is a vector that is pointing out from that cylinder, right? So it's pointing in every direction. I'm just going to draw it here at the top surface, but down here at the bottom, it would point like this. How would you define the angle theta? Again, if you go right here and you plot another vector dA, the angle theta would be this guy right here. Okay, it's the same angle theta that appears here. Maybe this is a little bit easier to write down the next expression. So let's write down an expression for cosine of the angle theta so we can eliminate that term. If that is my angle theta, cosine would be the adjacent over the hypotenuse. So I would look at an expression that looks like r divided by square root of r squared plus x squared. All right, so far so good. Now the next thing you can do now is substitute that into my expression over here. I can also substitute the expression for the field inside this expression. And let's go ahead and do that. So this is kind of getting to be quite long. I'll keep everything here under the integration sign. So first we have KQ. We'll factor out all the constants in just a minute. I'm going to have this term, r squared plus x squared. For cos theta, you could substitute this r over the same term, except that it's a square root. All right, and what about the vector dA, or the length dA? So what we're going to do now is consider this shaded orange area here, right? Because that electric field is going to have the same magnitude everywhere along this surface. So how would we actually write dA for this case? Well, it's going to have a certain circumference, and it has a certain thickness. The circumference is going to be 2 pi multiplied by r, and the thickness of that strip is going to be dx, right? Some small element dx. So let's go ahead now and substitute that inside here. So we get 2 pi r multiplied by dx. All right, we can now eliminate just this tube, and what are we going to be integrating over? We're going to integrate over the variable dx, and we're integrating dx or x rather, x is here, goes all the way from one side to the other. Now I'm considering here a cylinder that has a length 2r. So that means I'm going from minus r to r is the span of x, right? So that the total length of that cylinder is 2 times r in this specific case. All right, now we have to just simplify that expression. So let me go ahead, take out all the constant terms. So I get a 2 pi that comes out from over here. I get a k value. I get the charge q. I also get r is constant here. You get an r squared that comes out. And now we have to just rewrite this integral as minus r to plus r. Make sure I don't make any mistakes here. What is left now is dx divided by, now I can group all of these terms together, r squared plus x squared, and that is to the 3/2. Okay, so this is the expression that I need to evaluate, but I've done a lot of the work. Next thing we're going to do is we're going to focus on this integral. So let's go on the next page, and I'm going to work on this integral using trigonometric substitution. I think is kind of the easiest way. You can also look it up in an integral table, but we'll do it using trig substitution. So we're working on the highlighted integral right here. What we're going to do here is look at a triangle, and I could define the variable x as being r multiplied by tangent of that angle theta. R is a constant, which means if you differentiate with respect to x, then you may have to kind of work at this for a little bit, but you're going to get r. This is simply secant squared of theta d theta. All right, so we're kind of working our way back here. What we want to do now is what are going to be our limits of integration. Again, x goes from minus r to r. So that means that the angle theta, if you substitute x as r, x as minus r, is going to go from minus pi over 4 all the way to pi over 4. That means you're integrating 45-degree angle, right, from minus 45 to plus 45. Okay, so I think we're almost ready to substitute everything back in. Again, let's just worry about this integration. So this here is now going to be a change of variable. So this is minus pi over 4 to pi over 4. My dx term is simply this guy. That becomes r secant squared theta d theta. And now this term you have to be a little bit cautious when you start substituting into here. This is r squared plus x squared. This becomes r squared tangent squared of theta, and everything is still to the power of 3/2 here. Okay, one thing you can notice is I could factor out an r squared, or actually an r cubed from the bottom. And if you take out those r values, you should convince yourself you get a 1 over r squared. You have an r up here, you're going to have an r cubed from the bottom. Once you take it out of this, this bracket down here, and at the end we're left with the integral, again, of minus pi over 4 to pi over 4 of secant squared theta d theta divided by 1 plus tangent square theta, again to the 3/2. All right, we're not done. We're going to use some trigonometric identities. This term here at the bottom you are able to simplify, because one thing I remember from high school was 1 plus tangent squared of some angle. That simplifies to secant squared of theta. So that really helps us a lot, right? So at the end, this integral here, you can write as minus r, oh not r, my goodness, minus pi over 4 to pi over 4. All right, we're going to be left with secant squared theta over secant cube of theta, right? After I substitute this, I take care of these powers. All right, that's okay. So I have 1 over secant here as the term that I'm integrating. Well, that's an easy one. That is simply cos theta. So I can't forget the 1 over r squared term. So my last expression before I actually integrate, minus pi over 4 to pi over 4. Done a lot of work here of simply cos theta d theta. All right, let's go on the next page and finish this off and put it all together to get our final expression for that flux going through the side of the tube. All right, so I've made a substitution for that previously complicated looking integral into something that's a lot easier. First thing I'm going to do here is I had previously an r squared, and I have one that comes from here, so that's nice. That simplifies that. Let's go ahead and keep this expression going. What do we get? We get 2 pi k q. And now this integral is pretty straightforward. That's simply sine of theta. That's evaluated between minus pi over 4 to pi over 4. Okay, that one I actually know by heart, I think. Sine of 45, or pi over 4, minus sine of minus pi over 4. Keep going. 2 pi kq. This is square root of 2 over 2, minus and minus square root of 2 over 2. So at the end, that whole term here simply becomes positive square root of 2. Okay, that is my flux. Now, again, that constant k that appears here in the electric field, that one you can also eliminate if you wanted. 1 over 4 pi epsilon 0. You still have the root 2 here. And you can simplify this a little bit further. Cancel out the 2 pi, cancel out this. And I can't forget the charge. Oh boy, I'm trying to go fast here. Keep on forgetting terms. All right, so my final expression now through the sidewall. Let's see if this makes sense. Square root of 2. I'm still left with a 2 from over here. And I have the charge divided by epsilon 0. All right, so what gives me a little bit of comfort is that this term in the front, right, that fraction, that root 2 over 2, that's about 0.7. So thankfully that this number is less than 1, right? Because I know from Gauss's law, if I integrate over the entire surface, I have to have the charge enclosed, which is q divided by epsilon 0. All right, so this expression would be just through the side tube. Let's go now and work at the ends. Okay, what if I wanted to calculate the flux through the ends of the tube? We'll consider one, but it has to be the same for both tubes because the charge is right at the center of the tube. Let's go set up that integral. It's a little bit different from this one, but still pretty straightforward. All right, we're now going to consider the flux through one of these surfaces here. Consider the end cap over here. Again, we simply write down our expression for that electric flux. Again, E dot dA. I'll write that just in terms of the magnitudes of these vectors. It's E cos of theta multiplied by dA, all magnitudes here, and I'm only considering the integral through the end. So let's start by writing our expression for the electric field. Everything's a little bit different in this case, so we have kq. What is the distance now? So the distance is different, right, for every point here on this end. So this point here is going to be a certain distance away, but this distance is fixed, right? This is simply going to be half the length. If the length is 2r, the surface is a distance r away. So this is r squared plus. Now we're going to consider a ring, right? That's going to have a certain thickness dr. Okay, well, that ring is going to have a certain radius. So that's what kind of this term looks like, right? So this distance that I have as the red dashed line here, this is r squared plus little r squared. And when you square it for that electric field expression, that's what it looks like. All right, what about cos of the angle theta? Again, the angle theta is the angle between the field vector and the area vector. The area vector looks like this, right? It's perpendicular to that surface. Here's the angle theta. The angle theta is also the same angle here, so that's uppercase R over this square root term. So cos of the angle theta looks like this. R squared plus little r squared. All right, and the last expression here is the dA, right? What is the magnitude of that expression? Again, you're kind of looking at cylindrical coordinates. So the area here of a little shell that has a thickness dr, how would you actually write that? Well, the total length here would be 2 pi r. And the thickness is dr. So you have to substitute that over here, 2 pi r dr. Okay, let's keep working. So this is really what I'm trying to evaluate here, and I'm integrating over dr. Dr, or r, is going to go from 0 all the way to the end of this cylinder, right? And that cylinder here has a size uppercase R. So let's go ahead and take out some of the constant terms from this integral, just to clean it up a little bit. So we have 2 pi. What else? We have the k, we have the q. Those are kind of constant terms. Uppercase R, which is here. And now I can group everything else. So 0 all the way to the edge of that surface. What else? R dr, and everything else here is r squared plus little r squared to the 3/2. All right, so this one's a little bit easier than the previous case. The substitution, in order to evaluate this integral, I could just define u as being r squared plus little r squared. That means that du would be 2r dr. Now you can go ahead and right away you can substitute, because you can see we have r dr and we have r dr right here. So that makes that integral a little bit simpler. The limits of integration now are also going to change, because little r goes from 0 to r. That means that u is going to go from r squared, uppercase r squared, all the way to 2r squared. So I'm going to write down this final integral, and then we'll go on the next page and evaluate it. So we get 2 pi kq uppercase r. Change the limits of the integral. This goes from r squared all the way to 2r squared. R dr becomes du divided by 2. I'll just put the 2 over here. And this whole term here simply becomes u to the 3/2. Okay, now let's go on the next page and finish this calculation off and check the final result. Make sure it agrees with Gauss's law. All right, we're going to keep going here. So this term here simply becomes 2 pi kqr. I could take that factor of 2 out. And what I'm left with now is just this simple integral here. This becomes 1 over square root of u, right? U to the 1/2. And again, I have to divide also by minus 1/2, something like this. And that's evaluated between both of those limits. Well, let's just clean that up a little bit. The handwriting's kind of getting sloppy. Okay, let's take care of some of these factors here. We seem to have these 2's everywhere. This one goes here. What else? There's a negative sign. I can't forget about this one. Let me just eliminate it here, put it here in the front. All right, we're just about done. We substitute at the end. Now, it looks like it's negative, but don't worry about that. Everything's going to work out at the end as long as I do the math correctly. So let's evaluate these two limits. It's 1 divided by square root. You substitute the 2r squared here, and then minus the r squared in here. All right, so the flux through the end. Let me just write end like this. Now we can still simplify this a little bit more. 2 pi kqr. What does this term become? Oh, there's nothing I can do with the square root. I could take an r outside of that, and then minus 1 over r. Okay, now this simplifies nicely, because look it, I have an r here, I have an r here, and I have an r here. Let's also switch the order here so it kind of takes care of this negative sign right here. So my final expression for the end, the flux through the end, looks like this. 2 pi, again, don't forget about this, the 4 pi epsilon 0. Q, there's no r dependence anymore. And if I just switch this, this becomes 1 minus 1 over root 2. Those 2 pi's leave, and I'm left with the factor 2. All right, so my final answer now is q over epsilon 0. I have a factor of 1/2 here. And I'm left with this last term here in the bracket, 1 minus. Okay, this looks more complicated than the previous one. And it is, and that's okay. But again, this is only one of the ends, right? Let's go put it all together now, look at the different terms, and make sure that when I sum them up, I get the right answer. All right, so this is what we had. The tube, the sidewall here, we had root 2 divided by 2, q divided by epsilon 0, and the one end was this side. Now, if you remember what Gauss's law is, Gauss's law says that if I consider all of the surfaces, right, the total, right, through a closed surface, in that case, the total flux going through a closed surface is equal to how much charge is enclosed by this surface. In this case, it's q divided by epsilon 0. Well, let's consider our different results. How do I form a closed surface? Well, I have to consider the flux through the tube, and then plus 2 times the flux through the end. So let's go ahead and make sure that this result holds. Right? We did so much work here. So the tube result is just root 2 over 2, q over epsilon 0, plus. Now when I take this 2 and I multiply it, it's going to take care of this 1/2 factor. So let's not worry about that. So here I get Q over epsilon 0, and I'm left with this term here, 1 minus 1 divided by root 2. Now you can rewrite this term, right? Let's keep the first term, root 2. Okay. Now the next term, plus Q over epsilon 0. And now this term, if I multiply by square root of 2 in the numerator and the denominator, I'm going to get minus square root of 2 over 2, Q divided by epsilon 0. Now you can see that that term is the exact same as the first term through the tube. All right, and at the end, what are we left with? We have a verification here of Gauss's law. It wasn't the easiest closed surface to do the calculation, but we do have that if you consider all the different parts, all the different surfaces, that the total flux through this cylindrical surface is the charge that's enclosed divided by epsilon 0. All right, thanks for watching, folks.